Engineering and Technology in Department of Electronics and Communication. This video is about subject Microwave Engineering. So, in this video, we are going to learn about the microwave measurement. In the last video, you learned about how to measure the power. So we learned the various methods of measuring the high power, low power as well as the medium power. So now, today we are going to first of all measure how to measure the noise. Measurement of the noise. As you know that what is the noise? The noise is an unwanted signal and which will be appeared into the signal during the propagation, during the transmission. So how to measure that amount of the noise? So as we know that there are the n number of sources of the noise. So there are mainly the three types of the source of the noise. The first noise which is generated by the device. The noise which could be generated due to the random fluctuation and the thermal fluctuations of the electron inside the device, which is referred to as a thermal noise. So it's this kind of the noise. So noise generated by the device itself. The other category of the noise, that is the noise generated and added to the input signal before the device. Now as you know that during the propagation, the noise that can be added into the radio frequencies, the noise that could be added, and that we know that we are putting the device and we are not able to reduce that kind of the noise which would be directly coming from the sources, natural sources. So noise generated and added to the input signal before the device. And the another one, that is the environmental noise, which is externally generated. So these are the various kind of the noise which would be generated. So now we want to measure the noise. Now we have a very efficient device to measure the input signal and the noise level. So the device that we can use is a spectrum analyzer. Using the spectrum analyzer, all the components, the minute component that you can see easily and you can measure it out. So all that component to measure we can use the spectrum analyzer. Now here we'll see the block diagram of how to measure the noise using the spectrum analyzer. So now first the signal generator. The signal generator will generate the particular signal. Now here we have the spectrum analyzer. Now the device for which you want to measure the noise, so that device we need to put. So you can say that the device under test, meaning the device for which you want to measure the noise. So this is the device under the test between the spectrum analyzer and the signal generator. So now the device under the test that we will put, and the way the signal generator will generate the signal, and according to that we can measure the output onto the spectrum analyzer. So before doing the practical, what you can do? You can remove the device under the test and you can measure the ideal reading. So you can just connect the signal generator and the spectrum analyzer. Whatever the signal that comes from the signal generator that given to the spectrum analyzer, it gives you all the components, the ideal values of all the components. Now you can put the device under the test and you can measure the noise, and we can also find out the noise factor. As you know that you have learned in the communication other chapters that what does the meaning of the noise factor. So we can measure that the same way over here, the noise factor. So this is the one way to measure the noise. Now using the other thing, that is the ready-made noise figure meter is available. So we can also measure the noise using using the noise figure meter. Now here you can see the diagram that the input termination. Okay, input termination, okay, that is the terminating load that we can connect over here. The noise source that we are putting, which will generate the noise. And the test device means the device for which we need to measure the noise. Okay, so here we are giving the having the noise figure meter. Now the gating source, it will do the controlling of the input signals, okay, provided to the excess noise source, okay. And this is the indicator. This indicator will gives us the output of the noise, okay. So now it is about the measuring of the noise. Now the next is the parameter that we want to measure. It's a measurement of the quality factor. We have the cavities, we have the devices which is having the cavity, and we need to measure all that factor. Then we can do it by the measurement of the quality factor. So at the microwave frequency, okay, the accuracy measurement of the Q factor for cavities having very high Q is very difficult. As you know that we have already learned that the low frequency analysis, the high frequency analysis, okay, that things is totally different one, okay. So again, to measure this quality factor at the high frequency, okay, now it is very difficult. Now it is why, that is due to the fact that the 3 dB bandwidth of the cavity response curve is very small, okay. So there is a small fraction of the resonance frequency, and for that the finding out the Q value, okay, that's very difficult. So the measurement of the quality factor, okay, that we can do it by using the 3 methods. Which are those 3 methods? The first method is the transmission method. Second method is the impedance method. And the third method, that is the transient decay or the decrement method. Now the first of all, the transmission method for the Q measurement. What we can do? The microwave source which provides the high frequency signal. Here the cavity resonator, okay, that's the important device to measure the Q value. So we have the cavity resonator, and its output is given to the detector which will detect the particular frequency, and the power indicator or the measurement, okay, that can be done over here. So now here, as I said that the response curve is very small. So here you can see that this is the curve, that is the frequency versus the output in dB. Now you can see that this curve, that's very small, okay, and using the half power frequency of this resonance curve, okay, we can find it out. So by varying the frequency of the microwave source, okay, and keeping the signal level constant, the output level that can be measured. As well as we need to tune the cavity, okay, and we can tune the cavity, that is by keeping the signal and the frequency constant, and that way we can measure the output power, okay. So now we have the cavity resonator, and it's an important device to measure the quality factor. So it acts as a transmission device from which the microwave signal that passes, okay, and it reaches to the detector. So output signal is measured as the function of the frequency. So output of that cavity resonator, function of the frequency, and that gives the result that is in the response of the resonance curve. Okay, so we can find it out using the half power bandwidth, that is the 2W that can be obtained. So what is that? It's a 2W is equal to plus or minus 1 upon QL. And QL, it's a loaded Q value. Okay, so now what is the QL? that is the 1 upon 2 delta. Okay, delta, so it is the plus or minus omega upon 2 into omega minus omega 0. Now we know that if the coupling between the microwave source and the cavity detector and the cavity are neglected, then the QL value that is equal to Q0. It's an unloaded Q, and such kind of the system that is poor to measure the quality factor. So it is about the transmission method for the Q measurement. Now next is the measurement of the impedance at the microwave frequency. Now impedance at the microwave frequency. Okay, so impedance of the microwave frequency that can be find out by using the two methods. The first method is the slotted line method, and the second method that is to use the reflectometer. Okay, so first method using the slotted line. What we can do? That we have the microwave source. Microwave source given to the output of the microwave frequency given to the isolator. So all the signal that will travel in the one direction. We have a slotted line section, as you have seen all the components. So we have a slotted line section, and by using the probe you can measure the signal at the particular frequency, where the signal amplitude is high, where the signal amplitude is less. So by using the tunable probe, okay, what we can do? We can measure the signal. Also the slotted line, okay, the unknown load which is connected over there. Okay, so that you know that while the impedance that is the match, okay, the signal that can be passed through that. So here we have the detector mount, okay, which will detect the signal, and you can observe the signal onto the CRO. So this way, using the slotted line section, we can match the signals and we can find it out the impedance using the CRO. You know that my input signal which is traveling, after that my signal that is again coming back. So we know that what is my V maximum, what is my V minimum, and from that we can find it out. The second method, that is impedance measurement using the reflectometer. So we have again the microwave source. This microwave source which will generate the microwave frequency. Pass it through the isolator. Now reflectometer, that is made up of what? So here we have a 4-port directional coupler. So this is the port number 1, port number 2, port number 3 and the port number 4. Okay, and at the port number 4 we will connect the device under the test. Okay, now here the port number 4 connected with the device, and we need to connect the mesh termination so that the signal will not pass through the other block. So here we have terminated the block. Okay, now the port number 2 and the port number 3. Okay, onto the port number 2, the match termination is connected, and onto the port number 3, the detector mount is connected, and detector mount output which we are going to measure using the CRO. So now what happened? Then when the port number 2 which is connected with the match termination, and what happened? The power from the port number 1 which will be passed through the port number 3 and to the port number 4. Okay, and what we can do? That we can find it out the signal. Okay, so this way we can find it out the impedance using the reflectometer. So my P is equal to V reference upon V input. Okay, so SWR is equal to 1 plus rho upon 1 minus rho. Okay, and we can find it out from the reflection coefficient. We are able to find out the SWR value. Also we can find it out the ZL value. Okay, so this way we can find out the ZL is equal to Z0 in bracket 1 plus rho upon 1 minus rho. Z0 impedance, characteristics impedance, we are assuming that it's a 377 ohm, and we have the equation that is for the lambda. Lambda is equal to lambda C square root of 1 minus Z0 upon ZL. So these are all the equations which we studied earlier. Okay, so this way we can measure the impedance. Okay, so thank you very much everyone.